it's a great pleasure to introduce Eun-Ah Kim. So Eun-Ah is a theoretical physicist. She got her PhD in 2005 from the University of Illinois at Urbana-Champaign. She spent some years at Stanford as a postdoctoral researcher, and afterwards she moved to Cornell, where she started as an assistant professor, then became associate professor, and now she's a full professor of physics. So Eun-Ah is theoretical physics working in many different fields, and in particular working in the condensed matter physics in those systems that have collective states of matter that combine many interacting systems. And in particular, she's especially interested in strongly interacting systems, such as those that appear in high TC superconductors, topological phases, and other quantum materials. And in particular, she's working on some of the most recent developments in the theory of condensed matter physics. She also has very strong collaborations with leading experimental groups in quantum materials, and she has been leading also the new development in machine learning applied to condensed matter physics. So, and that is actually the topic of today's talk. So without anything else to say on my side, Eun-Ah, we really look forward to your talk, and thanks so much for giving the talk today.
All right. Thank you for the introduction, and thank you for giving me this opportunity to share. Very excited to be here. So I want to talk about interpretable machine learning of quantum emergence, and part of the talk, large part of the talk will be based on this paper that we recently posted on arXiv, and there is another paper that's in preparation that I'm very excited about. So emergence is a social phenomena. As a social phenomena, people, it's when a group of people, crowd, gather together and exhibit something that is beyond properties of individuals. Now, if you zoom inside, there is vibrant and mysterious social phenomena of electrons that's living in the environment of stadium that is materials, in the lattice, interacting with the lattice, degree of freedom, and so on. Now, the information content in the quantum materials, if you only think about a perfect crystal, for instance, here what I'm showing is cadmium oxide, is just a few hundred bits. That is, number of atoms and what is the crystal symmetry group. You can reduce it if you just reduce it down to a single unit cell. Perfect crystal is just a repetition of single unit cell, everything frozen. However, if you think about defects, crystalline defects, or any kind of faults, doping, orbital degree of freedom, charge degree of freedom, spin degree of freedom, collective phenomena, information content quickly goes up, and you can easily see when you have extensive amount of information, a piece of material that you're holding in your hand can carry information that is easily much more than the total information content in the Library of Congress. So the quest in the community has been to try to understand how different structures lead to vastly different properties, and to predict how to figure out a material that's going to exhibit exciting phenomena. And the general sort of unsaid understanding in the community has been that, okay, the information content is extensive, although most of us don't even try to quantify it. Therefore, let's try to gather as much information as possible. We develop new type of probing techniques. For instance, many different probes have gone to a scanning mode so that you can get not one number out of the sample, but many different numbers as a function of position. What has happened over the decades of effort is to collect more and more information, and where we are now in entering the age where we are not challenged so much by our ability to collect data, but more challenged by the volume of data. It's like drowning in the goodness of data. And we see that in many different places. For instance, the Hilbert space of quantum systems, even though we have our noisy small systems, the Hilbert space is exponential. And when you try to reconstruct the state from the measurements, you're battling the large dimensional space. Perhaps more close to the heart of some of you in this audience, tunneling density of states in 1962 was measured using a macroscopic tunnel junction. And so there is one big junction, you apply voltage, there's one number you measure as you change the voltage. So in this kind of setting, people made major findings, such as this very famous, well-known paper in the superconductivity community. This is density of states of this superconductor, which we now call BCS superconductor. They found this suppression of the density of state and sharp peak, but it's not only those features. When you have a single curve, theorists have not been able to understand even the subtle features and confirm that is evidence that this BCS mechanism of phonon-mediated superconductivity is in play. Now, fast forward to 2000s, instead of making a single macroscopic tunnel junction, we make atomic scale junctions and many of them. So at each position, you make the measurement of those curves, and now you have this three-dimensional data set. And you can open up a standard solid-state textbook such as Ashford and Mermin. You're not going to find guidance on what to do with data like this, how to connect this data to some theoretical insight. In reciprocal space, X-ray diffraction in 1913, this X-ray had been around for a little bit at this point, but it was this paper by father and son Bragg and Bragg where they were able to have a first successful interpretation, analysis of this data, consisting of near 3 keys. Okay, they had the very first successful forward model, which is to guess what you cannot see by your eye, that perhaps there are atoms forming a lattice like this. If that was the case, we can introduce a single parameter D, which is the insight that we are gaining about this atomic scale system, and use this condition to associate the peak angle as you rotate the sample by hand with this parameter D. Now again, fast forward to today's infrastructure, today's facilities, and what you get is automated rotation, of course, but hundreds of thousands of brilliant zones being covered here, these little honeycombs are brilliant zones. And you have the sensitivity of your detectors that are no longer films, which gives you a huge dynamic range. So now my group has been, over the course of last couple of years, really wrestling with the idea of how do we make the most of this abundance of complex data. Instead of drowning in the large volume or complexity or richness of data, we would like to be able to get insight out of it. And so we've explored several different frontiers. Perhaps most exciting of them was this paper in Nature, where we were able to use artificial neural network to analyze STM data on under the Preprocessing, and we were able to analyze 12 years of repository of data from Seamus Davis's group, and we were able to do hypothesis testing on this data set, objectively testing what kind of pattern, what kind of motifs are most visible in the data. Not visible to my eye, but visible to a more objective machine. Of course, we all see the same thing, and the patterns jump out to us. But when it's human impression, human recognition, it has to go through our brain where other things get mixed in with what we just saw with our eyes. And when we used neural network to analyze data, we found that there was something that's very robust over a wide range of doping that is a commensurate charge density wave pattern being most dominant, which is consistent with strong coupling picture of this underdoped data set. We've also looked at resonant ultrasound spectroscopy in uranium ruthenium silicon 2 and revealed aspects of the hidden order parameter, trying to constrain it. We've looked at data from IBM-Q machine doing tomography based on natural language processing scheme. This is a project that is in preparation, analyzing scanning transmission electron microscopy data. We've also looked at simulated data of non-Fermi liquid transport near 2 different quantum critical points. Most lately, posted to archive is this paper where we use unsupervised machine learning to look at X-ray diffraction data. In all of these, the theme is trying to use data science tools, principle-based data science tools such as probabilistic modeling or deep neural network to try to connect experimental data to theoretical understanding. Now, trying to connect the experimental data with theoretical understanding and using data science tools in physics comes with a particular challenge compared to, say, self-driving car or cars or movie recommendation that we're familiar with. Of course, self-driving cars can put people's lives at risk. So obviously, this is it's a problem that needs serious solution. But physics has had a long tradition, which also, in a way, supported people's lives. Rockets were we went to the moon using the principle of physics that we understand, and that's really the challenge. As physicists, we are used to connecting simple principles with complex reality of data successfully doing so through the long history and tradition of physics. We are used to taking reality of data and trying to come up with a simple understanding. We've been doing that since Galileo and making predictions on where things are going to go. Now, in data science language, going from complexity of real data to simple principles is called regression, and going from simple principles to making predictions is called generative modeling. So it is plausible that we can use data science tools and learn from some of those modalities and gain most from the data that we can take today. But challenge is that we are used to, we have a tradition of being able to go from this kind of simple, beautiful understanding mathematics to some object bouncing around. And we have a tradition of understanding how to go from here to there pretty much all the way through. So biggest complaint people have when one is introduced to data science tools or machine learning tools is that, I don't want to believe a black box. So one thing that we've learned to be very important is that interpretability. We need to be able to interpret what we are seeing within the framework of physics. Only then we can succeed in machine learning application of quantum matter. One thing that I like to tell people when those who are new to this data science tools is that tools are purpose driven. So these are some tools that we can see if you go to Home Depot. These are both wonderful power tools. However, if you want to hang a frame on the wall, you wouldn't pull out your drill or power saw, but what would be most useful would be a hammer. So what's really important is to know your tools, or at least you need to know your problem statement. Once you know the problem statement, like you go to Home Depot, you can search around for a tool that would work the best for you. And in thinking about a tool that so-called work the best for you, it's important to remember what your aims are. So for instance, this heavy-duty blender is a wonderful tool if you want to make smoothie. But if you want to make guacamole and you want to savor every ingredient that's in there, you would want to use a tool that in a way looks like a Stone Age tool. Nevertheless, is pretty expensive these days. Now it's kind of like making guacamole. When I think about some of the data science approaches that we're taking, we always try to make sure that we use kind of minimalistic approach, not only because they are most failure, most like they're safest, most reliable, but and often fastest. But it's really because when we use minimalistic approaches, we are most likely to be able to interpret the results within our physics principles, within our framework. So first topic that I want to tell you a little bit more in detail is unsupervised machine learning for voluminous X-ray diffraction data. We developed a tool we dubbed XTech, which is X-ray diffraction temperature clustering. And this was really led by my former graduate student, Jordan. We had a great fortune of working with really interdisciplinary team involving computer scientists at Cornell, X-ray experimentalists at CHEST at Argonne National Lab. So what are we after when we are looking at X-ray data? We see a bunch of intensities. We want to learn what's happening in atomic scale from those intensities. And as a physicist and a theorist, what I really want to know is what kind of emergent phenomena, spontaneous symmetry breaking, is occurring. So if you are considering, for the sake of illustration, one-dimensional lattice with two sites within unit cell, a fully symmetric, undistorted system looks like this, and charge density wave with period of 2a, resulting from the orange atoms, every other one being displaced in opposite directions, would lead to the following X-ray intensity. You now get super lattice peaks at positions where you didn't have, but there's also a form factor which gives you the Brillouin zone dependence. What about distortion or ordering symmetry breaking that does not change the unit cell size? We call those intra-unit cell order, which we first started to discuss in the context of cuprates and intra-unit cell nematicity. Intra-unit cell order is only reflected in the form factor. So in this example, we have all the orange atoms being displaced in one direction. Now with this, the symmetry is lowered, but the unit cell size has not changed. So you don't see any new peaks, but you see the form factor effect. Now, when you don't have this picture and all you have is this, and you're trying to figure out what is going on in the system, that's the inverse problem X-ray and TEM and many different neutron many different diffraction probes face. Now, how are we to find what's going on when you have 100,000 peaks, not 3 peaks that Bragg's had, right? Bragg and Bragg had 3 peaks to deal with, and here we have 100,000 peaks. So when drowning in this volume of goodness of data, drowning in the richness of data, we thought about, I personally can relate to another experience of drowning in the richness and goodness. This is the experience that I think about. Under the pandemic, with kids at home, I spend way too much time sorting through a big pile of Lego. And many parents have love-hate relationship with Lego. If you are asked to find a particular piece, you quickly learn sorting them through one piece at a time, picking up a piece and inspecting by eye and dropping or choosing is really somehow really not a very effective way. And you can do a quick calculation of probability and figure out the odds. Now, after being asked to do this, too many times, you quickly develop a strategy. Okay, let me not just work with a big pile. Let me sort them, and maybe dream of keeping them sorted. But if you want to find some piece, at least even for one time, you want to sort them first. And if you're looking for a yellow piece, you only need to look inside this yellow bin, and maybe you'll further down sort it by shape, and then that's how you can go for the piece that you want. Now, but what do we do with X-ray data? What do we do with quantum matter data when we don't have obvious sorting criteria like color or shape? What should be our sorting criteria? So one thing that we've developed is the idea that if you have a control parameter, for instance, temperature. So if you're looking for an emergent phenomena, symmetry breaking, it's a phenomena that's exhibiting as a result of competition between energy or Hamiltonian and entropy. And what's controlling the balance between entropy and Hamiltonian is temperature. So you expect, without necessarily knowing how to model, and this is the part that you gain by working with data science tools. I don't necessarily need to know I don't need to have a theory yet of the temperature dependence. All I need to know is that this gross level, this kind of more foundational level, temperature is controlling what's intrinsic in the system and the random desire, right? So we can anticipate different points in reciprocal space would have different temperature dependence if depending on whether they are participating in some collective ordering or not. So now we're going to treat the intensity that is a function of different reciprocal space points and the temperature as if they are a population, and each person has their history, time trajectory. Here, each point in reciprocal space is going to have temperature trajectory. So now, if you look at temperature evolution of plane of reciprocal space data, of X-ray data, this is titanium diselenide. This is the material that we use to develop X-Tech. It's a material that is well known to have charge density wave. We know a lot about the material, and that was an ideal data set to what we call burn to develop our tool. Now, if you know where to look, so that is because you have a three-dimensional intensity distribution, if you know which plane to look, you can see the following temperature evolution. At high temperature, you have kind of a blurry data. But then as you lower the temperature, you start to see some peaks show up. And this is a plane without the lattice Bragg peak. That's why it's all blurry at high temperature. And then you further lower the temperature, you see the sharpening of these peaks. This is a super lattice peak because it's in a plane where there is no Bragg peak. Half plane, right here, a half plane. But if you didn't know where to look, what you would do is take the temperature dependence of intensities at every single Q point in your three-dimensional data set. Okay, so you have a grid of Q points and intensity having recorded by your detector as a function of temperature, and you look at it, and that's the mess you have. And this is like my box of unfortunate box of Legos. So first thing my student Jordan realized was that, okay, this has noise of widely varying scale. You see the scale bar here, 10,000 from 0, and there is a lot happening down here actually. So he came up with sort of a principled thresholding scheme to remove much of the space in between, because reciprocal space data is very sparse. After the thresholding, we're left with this kind of Q points, remaining Q points to follow. And now, in keeping track of the temperature evolution of those Q points, the approach that we have adopted was an approach that was very successful in speaker verification. It's kind of early day speaker verification tool. So when you have several people speaking, or the noise canceling. Noise canceling, I guess, is simpler because you're trying to cancel some particular frequency. When you have multiple speakers speaking, right? So if it's a voice train of multiple speakers, and some of you, if you have experiences with one of these AI secretary devices, AI devices at home, like Alexa and Siri and whatnot, you will know that some of them are capable of telling different family members' voices. So how do you do that? In this compilation of voice trains, you can discover that there is one speaker and another speaker. And that's done without somebody giving the model of the speaker's voice train, because we don't really know that. But the device is supposed to discover that particular qualitative features. So the specific approach we've used is what's called Gaussian Mixture Model. So in Gaussian Mixture Model, the goal is to, in our application of Gaussian Mixture Model in XTech, the goal is to take the preprocessed temperature series. So I'm using this tilde notation and boldface to mean that this is a vector, meaning so at each reciprocal space point that I've decided to follow, there is so many temperature data set, so that forms a vector. And you are conjecturing that there to be multivariate normal distribution. So we're assuming that there is a normal distribution with unknown mean and unknown variance. Those are to be learned. And moreover, there are k different normal distributions, and each of my data points, the population, the percentage that is subject to census right now, let's say my Q point, particular Q point, is going to belong to one of them with the likelihood, the weight pi of k. So it's just like fitting. It's a fitting in the large dimensional space, but not trying to fit with one function, but fitting, allowing for multiple functions to be at play and discovering those functions. And the function is not linear or polynomial, but Gaussian. And the fitting, this model, it converges using the expectation maximization algorithm, which really tries to maximize this log likelihood. Likelihood that my data came from a particular normal distribution, a collection of normal distributions with the weight distribution. Okay, so you try to make it most likely, then by making it most likely, you found the distribution that best captures your data. And once the algorithm has converged, we have this cluster assignments. Okay, so once we developed this approach to the using the titanium diselenide data, we've applied this to pyrochlore cadmium renate. It's a pyrochlore superconductor, first known pyrochlore superconductor, and it has a phase diagram where high temperature phase, symmetry of the high temperature phase is well known. But at about 200 Kelvin, it goes through a very well-defined, sharp, continuous phase transition. And this lower temperature phase, and what the lowest temperature phase is, and what this blip means is still not very well understood. Now, superconductivity occurs somewhere down here out of this phase, and it is obviously of interest to try to understand these phases. The difficulty is that these are structural transitions with extremely small distortions. And the big puzzle has been whether this phase should be described by a two-dimensional EU order parameter or one-dimensional T2U order parameter. So we have, together with Argonne National Lab colleagues, we have analyzed about 8 terabytes of data. And the whole 8 terabytes of data spanning 100,000 brilliant zones get captured by our X-Tech into this simple form. This is what we get when we assume 2 clusters. And what you're seeing is that this clustering mean and variance. It says that there are some Q points that seem to be best captured by this kind of behavior as a function of temperature, the intensity rising, suddenly starting to kind of jump up around 200 Kelvin. And then there's another cluster that is showing much more gentler dependence. So now I emphasize the need for interpreting, which is why I like to make guacamole in Morel and Pestle. Here, the interpretation is very easy because all you have to do is to look at, once you converge, look at where these Q points came from. Some of the Q points were assigned to this cluster, some were assigned to this cluster. Where did they come from? We just look at them in the reciprocal space. And this is a result of treating the region near each Bragg peak to be one cluster. That's why they're by design simple. But what you see is that all the purple peaks came from these positions. There is a very clear selection rule that you can quickly discover. And the selection rule is consistent with EU order parameter. And the fact that we've scanned every part of the data gave us confidence that we haven't left anything out. Now then we wanted to further investigate what's happening inside these peaks. So we opened them up and now ran clustering with allowing for the number of clusters to be varying. So we found assuming 2 cluster and 3 cluster and 4 cluster made differences, but by the time we went above 4, the results didn't look any different. There were no differences. So we concluded, okay, 4 cluster is what's naturally in the data. That's what's actually in the data. Now, looking at the clustering result with 4 clusters, for the temperatures below 150, avoiding the whole critical behavior at 200, what we found was the surprising result. Surprisingly, regions of each blob, each peak, like this is extremely high resolution data. So around each Bragg peak there was a whole region. Surprisingly, the center of the peak and the diffuse region around it clustered into different clusters. We didn't tell anything to the algorithm. This is what we discovered. Every single center of the peak generally had relatively mild temperature dependence once they have passed through the second order transition at 200 Kelvin. However, around each peak, there were whole diffuse region. And in particular, these red regions show higher intensity extended over the entire phase 2. And then they drop. And as they drop, the diffusion intensity and the blue regions went up. By looking at where they came from, we could figure out the selection rule that informed us that this red region showing intensity has to do with particular out-of-phase motion between cadmium and rhenium. We've identified which atoms are moving in what direction, out of phase, in phase, when these atoms are all within a single unit cell. So we've learned intra-unit cell arrangements. And the fact that this is really, there is something going on here is evident in this raw data. This raw data shows there is intensity associated with this diffuse region that is extending over the entire phase 2. Now, this was all good, but my X-ray colleagues were, they were puzzled. My colleagues were saying, like, but this doesn't make sense. We've never seen this before. You know, this is not critical scattering. This is so far from critical region. What is this? And that's when we realized, oh, this is a fluctuation that is extending over the entire ordered phase. And you get that when you have a two-dimensional order parameter and have a Goldstone mode. So this is a detection of Goldstone mode. And in order to have a Goldstone mode, your order parameter has to be two-dimensional. So the only option here would be EU order parameter. So this is the first instance of successfully detecting Goldstone mode fluctuations using X-ray data. And what we're really excited about XTech is that this, because there is nothing that we've done that's so particularly designed for this particular data set, we are confident that this should be applicable to neutron scattering or any other neutron scattering or other X-ray data set. So right now we're working on integrating this into the facilities. Now switching gears to a real space probe, we've had our first excitement with STM data, and now we are starting to look at quantum gas microscopy data. So this work was led by my then first year, now second year student, Cole Miles, rather amazing. He got all these results as a first year graduate student. We've been collaborating with Eugene Demler's group at Harvard and working together with my colleagues in computer science. So quantum gas microscopy is the leading tool for studying ultra cold atoms. Now, these are, if not the same thing as, it's not the same thing as studying an actual material, but as you'll see that the approach that we've developed does not care how whether the data was obtained from quantum gas microscopy or on the real data. So we'd be very interested in trying to expand the applicability of this correlation convolutional neural network, CCNN, to other types of image-like quantum matter data. So quantum gas microscopy is the best tool for studying ultra-cold atoms that are simulating quantum matter. And the community of cold atoms have now finally reached low enough temperatures to study magnetism and to also start exploring pseudo-gap and strange metal phenomena. But the trouble is, what they get out of the microscopy are snapshots. That's not expectation value. And as far as the snapshots go, the outcome from two radically different theoretical ideas look not so different. So this is a snapshot one would get under geometric string theory, where you say, okay, you dope a hole into an antiferromagnetic background. As the hole moves, if this was original position, as the hole moves, there is a whole string that it is dragging of string of wrong bonds. This is a wrong bond, this is a wrong bond, and this is a wrong bond. Pi flux theory starts from RVB, resonating valence bond picture, where you say, okay, you have this singlet pairs that are in superposition, and you're taking some of the hole, doping it with holes. Now, these two theories are very, very different at the level of ideas, at the level of how you think about the system, where they come from, what would they mean. But at the level of quantum gas microscopy, it's hard to tell how they're different. If they are different, they're probably different, but we didn't know how to think about them. There have been a lot of efforts in the community to use off-the-shelf CNN, and the problem with using off-the-shelf CNN is a little bit like, you know, trying to hang a frame on the wall with a drill. You can do it, but it's awkward and it's overkill. So awkwardness in this case is not just an inconvenience, it's a black box, so you don't know what it is learning. Overkill is an overkill, you're overdoing it. So what is our alternative? We have proposed correlation CNN. This is correlation convolutional neural network. The idea is to do the convolution like one does with any image processing, which involves some filters that you learn. But instead of just throwing that convolution into standard nonlinear functions, standard here is what people found to be useful, working well in images. When you're dealing with images of faces, images of clothing, nobody said that's going to work well in quantum metadata. So instead of doing that, we're going to take that convolution layer, that's C, and we're going to look at its powers, polynomials, which is a systematic way of thinking about the nonlinearities, which is necessary to get expressions. But here, when we do polynomials, the nonlinearity we are getting here is going to give us higher order correlation function. So nth order polynomial of convolution we're considering is amounting to an nth order correlation function. So we build those correlation functions in this kind of cascading scheme. And then once we have a trained neural network, we can learn which of these features, this got all averaged into 4 numbers, associated with a particular filter that was learned. So we figure out, fixing the filters, which of those features led to improvement in accuracy that's meaningful. So we see accuracy going up. This is called regularization path analysis. You're allowing each of these information to participate in the decision making in this decision making step, and you see the accuracy go up a bunch when this 4th order correlator of this filter is allowed, and 4th order correlator of this other filter. There, we use 2 filters for this particular example, trying to tell apart geometric string from pi flux theory. And then we see a little bit of enhancement in accuracy, performance go up with 2nd order filters. But what we see also is that the 1st order filter and the 3rd order filter plays hardly any role. So now knowing this gave us a way to think about these filters in the language that we are used to thinking about as physicists. So the 4th order filter of 4th order correlation, C4, of this particular filter in spin up, spin down whole channel, to see what that means in terms of motifs. What we are seeing, what we have to do is to take 4 pixels, for instance, take these 4 pixels, and and for each of those pixels, 4 because I'm looking at 4th order correlator, I can take the intensity from one of the 3 channels. So if I take the intensity from the down channel, and here down channel, here up channel, here up channel, I get this pattern. And the intensity darkness here is showing the importance of those pixels. And this way, we were able to figure out the motifs. And then we could say, okay, now do these motifs ring any bell? Are these something that we would anticipate? And we realized, yes, indeed, this kind of motif and this kind of motif is exactly what you would get when you, in a geometric string theory, when you have this wake behind the hole. So you see one motif that looks like rotated version of this, and you see another motif here that's a rotated version of this. So we could tell that the neural network learned meaningful features because these are the this is what makes sense with a more fundamental theoretical view of each of these hypotheses. So this was done with simulated data, with allowing for the system to learn two filters, and the outcome was binary, whether it is a geometric string or if it is not, it was pipe flux. But when we then we applied the network that was trained on the simulated data, that label simulated data, and try to apply it to the experimental data. And what we figured out when we did that was that the experimental data which we used was lacking in a channel of information, and also the experimentalists at the time of taking the data didn't have a good way of knowing their hole density. So what the neural network plot on was not whether this kind of motifs are being shown, but it just simply went with the hole density information, which was not quite right. We didn't have a correct understanding in the data. So we realized that with that amount of information in the experimental data at the time, it's actually not meaningful to try to use neural network. And this is the first time where people could in a principled way say not only whether I'm learning something, but moreover, is this approach giving us a meaningful insight? And we believe this is really, there are a lot of people trying to use neural network for image-like data, and I think more and more being able to give a principled insight into not just that, hey, I've succeeded in using neural network and I got some output, but I know how the shots were called, and I believe this to be meaningful because I can make sense out of it within the framework of physics. So to summarize, I've talked about interpretable machine learning of quantum emergence, and I talked about specifically XTEC, XRD temperature series clustering, and correlation convolutional neural network, how we can learn the correlation functions that are important. In the case of this quantum gas microscopy data of fermionic Hubbard model, underdoped fermionic Hubbard model, what we learned was that it was fourth order correlation that's useful and meaningful, which people didn't know to think about. We all know linear, which is like the order parameter. Second order correlation is what we typically think of as a correlation function. Fourth order correlation function, we never thought that would be important. But we learned it was important, and once we learned, we could make sense of it, that it makes sense. So this is the kind of synergy and back and forth between data science tools and us as domain scientists we can have. And I believe it is very important to own our problems, our questions, and to recognize that we own the data and we own the questions, and knowing the objective, knowing the question that you want to answer, you can, if you go into the data science tools, that are many open source tools are available. And if you go knowing what you are after, I think these tools can really greatly help us make the most of the richness that we are now experiencing. Now, in closing, I want to show that this image is a way of expressing how I think about data science and machine learning. Now, often when I give colloquia, sometimes I get a question like, well, but automation takes job away. Yes, automation takes job away, but humanity have been pushing automation because we have a desire to do what's less manual and more thinking, right? So this is a scene towards the end of this wonderful movie called Hidden Figures. And the marching group of women were the group of West area computers, human computers, before we had machine computers. These were last generation human computers. When the IBM 7090 was introduced, those who didn't learn to program IBM 7090 lost their jobs to the computer. But those who learned to program IBM 7090, which although it's a wonderful machine, needed to be programmed, became programmers. So the idea is that we have the richness of data, and there are tools out there, and it's up to us to learn how to use those tools to make advancements in science and solve long-standing problems. And in order to make meaningful contribution coming back to the community, it's really important to always to be able to interpret what you're doing within the language and framework of physics. Only then you can actually make the science move forward. So with that, thank you for your attention and patience with all this technical somehow glitches that I was having this particular morning. Thank you very much.
Thank you, Eun-Ah, for this really wonderful talk and for showing us all these very impressive demonstrations of machine learning, both for experimental data and for simulated data, and of course for this very inspiring message for the use of machine learning in condensed matter. So we have now time for questions. So if you have any question, you can either raise your hand in the participants button, or you can just write it in the chat. So perhaps I can make the first question.
Sure.
So you showed, yeah. So you showed two examples, right? The first one was, let's say, 3-dimensional data, and the second one was, let's say, 2-dimensional data,
right?
Basically, right? So let's say, is there, let's say, some substantial difference that one needs to keep in mind when dealing with data of different dimensionalities? So for example, if I wanted to work with data that lives in a space in which I cannot properly say which dimensionality it has, would I keep something in mind for that?
So I think that depends. The way, if for an image-like data, if you're looking for, what do we mean by image-like? That means we're looking for spatial correlations in the space the data was taken. Then with convolutional neural networks or similar kind of approaches, you have a filter that is kind of rastering through the system like this. So 1D, you will just go once. If it's 2D, you're going to go back and forth. Now you need to be able to learn that correlation that is in that snaking farther along, but that's okay. And you can continue that into 3D, 4D. But if your data has a structure that is like multidimensional, let's say it's 4D, right? But there is one set of 2-dimension or another set of 2-dimension that they're not really connected. If there's a structure like that, you want to make sure you build that into your architecture. So I think it depends on what is important in your data. But general but nothing's really quite stopping you from working on higher dimensional data sets. For instance, for scanning transmission electron microscopy, STEM data we're working on right now. We are using 4D convolutional neural network. We developed it because there were no 4D, there were 3D convolutional neural networks. But it was an obvious and doable extension of 3D.
Yeah. All right. Thanks a lot. So there's a question in the chat, which is if you could explain what a quantum gas microscope is. Yeah, because there's some people.
Yeah. Good. Okay. Now I'm not going to do a great job because I'm not an expert on quantum gas microscopy myself. One thing that's really fun about having learned data science tools a little bit ahead of other people, is that I get to work on many different types of data and learn new types of measurements. So this is how quantum gas microscopy works. Can you see my screen? I'm not going to go into the presentation mode. Can you see my screen?
Yes,
yeah.
we can see it.
So the atoms live in this kind of Eckarton potential. And these potentials are set up optically. And the microscopy is done through optics here. And each image here, this is the high resolution imaging, each image imaging interacts with the system. So after you take one image, you've kind of lost the system. Now this is the grid view, and if you're imaging in a particular mode, here green could mean spin up and black could mean spin down or no particle. So this kind of a black and white image is what you get out of quantum gas microscopy. I hope that answers Andre's question.
Yes, I think that this answers the question. So yeah, I don't know if there are any other questions. I don't see any hand raised in the participants button, and I think that there's...
Yeah, maybe I can ask a question. So okay, so in basically you put in some well, physical intuition or theoretical understanding first into the machine learning model, and then you get, how to say, you get sensible results out.
Right.
But can you somehow tell when you are doing this that if there's some completely different phenomenon that is controlling what happens in the measurement, that if your model is seems to fit but doesn't capture the physics right?
Right.
Can you somehow tell this?
Yeah. So so the two machine learning examples that I showed, one was unsupervised, X-ray was unsupervised. Quantum gas microscopy was supervised, but it was interpretable. Because it was interpretable, we were able to tell that applying that neural network to the experimental data was failing. The neural network said, this looks like option A that you gave me. But then we were able to look inside and say, see why it was saying option A. And we figured out it was saying option A for the reasons that are not meaningful. So then we declared failure. For the X-ray case, we do the clustering and we look at the results outcome in the reciprocal space. And then we can try to see whether this is something that we know how to think about. So the cadmium renate data, 8 terabytes, it took us 15 minutes, 15 minutes to run the algorithm, okay? And then we got this result, which had regions inside the Bragg peak, single Bragg peak neighborhood being clustered into 2 different clusters. And my colleagues, experimentalist colleagues, Ray and colleagues said, this doesn't make sense. We never do this. We never think of a Bragg peak to be the center and the neighboring region. We don't know how to make sense out of it. And I said, but this is what's going on in the data. And they said, but it doesn't make sense. We've never seen this before. And I said, but this is actually in there. So then I said, we got to figure this out because this is actually happening in the data. So we sat on trying to make sense out of it for 3 months. And then we realized we can think about this in terms of the Goldstone mode. Now, yes, it still took us 3 months to get to the science in that case. When it's something that we already know how to think about, like charge density wave, we just discovered that charge density wave order parameter just like that. However, the typical modality of how things work with this kind of data set is that people take data for like 2 nights, right? Now the facilities are so wonderful. People take 2 days of beam time, take data. They go home, start looking at it this way, looking at it that way, like me facing my gigantic Lego box, picking up 1 piece at a time, people do this for 6 months, a year, but then you cannot spend one graduate student postdoc life, for forever. So you look for what you can look, and if you don't find it, you give up. And if I give up, I'm just telling my kid, okay, I'm going to buy you a new Lego set, right? So when an experimentalist give up, they've given up on that beam time, they're going out to much more expensive new Lego set, which is a whole new sample. So our goal is, this was in a development stage. Now we know at least two things that the tool can do. We can discover order parameter. We know how to discover the fluctuations. And we are trying to make it available to a broader group of people by integrating into the facilities, so that my dream is these poor graduate students, postdocs come to the facility, they take data, go for a coffee break, come back and find whether they've seen something or they have to change something, right? If you look like you've seen something, but maybe your temperature range could cover a little more, you take new data right there. So that's what I'm really excited about, this 15-minute. Although sometimes it took us 3 months afterwards. I hope that it answers your question.
Yeah, thanks.
Yeah, so there's one more question in the chat, which is if there's a paper associated with the correlation convolution neural network.
Coming. It's going to be out in, I don't know, within a week, I think, I hope. Yeah, we're now having final rounds of iteration, but it's going to be coming out very soon. When it comes out, when we post it on the archive, I will advertise it on my Twitter. So if you're a Twitter generation, that'll be one way to find out.
Yeah, and there's another question in the chat now, which is how
do you know?
How do you know if the outcome of data analysis with machine learning is reliable?
Right.
Wouldn't you always need a different method to test if the outcome is reliable?
Right. So that's a very good question. So that different method is human inspection. But once you've nailed it down to the what you found, right? So neural network or my X-Tech gives me an outcome, okay? And then it says, okay, this is a part that's interesting and important. And these are the parts that in my humble view are unimportant, okay? Then I don't have to just say, my neural network told me that these are exciting things and write a paper. No, I would see what it found. I will look at it, and it's kind of like, in my view, these are like my little minions, right? So I look at what it found, and it's often very simple to see whether it makes sense or not. Like for X-ray, if the X-Tech can find what's called streaking, the measurement noise, it can find misalignment, it can find some activity in several labs down the road. I don't know, maybe something blew up or something, right? All of those things will show up. But what it picks up is a small fraction of the overall. So now I have a select things that I can look with my eyes or expert eye and decide, is this really a discovery? And some of those things that we found were, no, it's a well-known blip. And then some of them we found, wow, this is something new we didn't know about. I hope that answers your question, Rebecca.
Can I ask one?
Yeah, please go ahead.
Do you have a plan to study time evolution?
Absolutely.
Yeah,
Absolutely.
that kind of interesting, especially.
Yeah, time evolution is very interesting. So I have a collaboration with Seamus. I know Seamus spoke in the colloquium recently, I guess last time.
Mm-hmm.
So Seamus is studying this monopole, like with his spectrometry. He's studying the spin ice and materials that are expected to have emergent monopoles, magnetic monopoles, right? And the data he's taking is in time domain. He's got time series data, but because he didn't have a good way of analyzing time series data, they Fourier transform. And they compare the Fourier transform with Monte Carlo data, which also gets Fourier transformed. And you know, I have nothing against Fourier in particular, but there are some things that get lost when you have Fourier transform. What's really visible in Fourier transform is the regularity. If you have a very nice sinusoidal wave, you get a nice peak. But if you have something that is more firing kind of motion, that's not something Fourier transform is particularly good at finding. So we are working on trying to develop time sequence based.
Yeah, I mean, it's about predictability, especially.
Yeah.
So, especially a neural network or devices that sort of, you know, similar to that, like memristors and so forth. So sometimes certain activity would have certain times, I mean, would have certain evolution.
Right.
One can predict it, but of course, to describe this vast amount of data, it's really difficult.
Right. Yeah. So absolutely, we're interested. Yeah.
Thank you.
All right, so if there are no more questions, I think that we can start closing the session today. So first of all, thank you so much, Eun-Ah, for this wonderful talk and for these very inspiring results on machine learning and for this very nice message. Thank you, everybody, for joining the colloquium today. And remember that the next colloquium will be November 2nd by Yuanbo Sang. And with this, thank you very much, Eun-Ah.
Thank you.
And see you next time.
Bye.